Hello, I'm Siti Hauruslan. I'm presenting a paper by my student Gu Ziyin. The paper entitled Low Power High Speed 130 nanometer Magnitude Comparator using 13 transistor hybrid full adder. First, we look into what is a magnitude comparator. It is actually a device or circuit that compare two binary numbers. In this example, we have A and B. Each is with n bit. And if we compare these two, we can have either A less than B, A equal to B, or A greater than B. Comparator circuit is needed in analog to digital converter, ADC, and it is also an important circuit in arithmetic logic unit, ALU, or in digital signal processing, DSP, communication and computing sorting, and high-speed data processor. So meaning that it is an important circuit. When we are comparing two-bit binary number, a short decision must be taken, and the problem is when the number are a very long number, meaning that for example you have 64 bits number. So the time taken to compare those two numbers, the delay is quite significant. So you must shorten the delay time for a longer bit magnitude comparator. In this example, I'm showing only 4 bits. For example, A is 1100 and B is 0010. And if I compare these two, the answer will be A greater than B. Since it is a 4-bit numbers, so the time taken will be shorter. And another important thing that we must consider when we are designing a comparator circuit is the power consumed by the circuit. Most portable circuit will need a battery, and if you want to prolong the battery life of the circuit, so we must make sure that the design circuit must consume less power. So for the magnitude comparator, we'll have 3 output, A less than B, A equal to B, A greater than B. And since this is a digital circuit, we'll have output 1 when A less than B, A equal to B, or A greater than B. So in this design, we are finding a technique how to design a very low power, but at the same time, we are having a high-speed comparator. To have a low power, we must use a power supply. So in this design, we are using 1.2 volt supply. And the CMOS technology selection, we are using 130 nanometer CMOS technology. And we design the circuit using Cadence EDA tools. First, we start with the schematic simulation. We must simulate the circuit, and if it is successful, then we can continue with the layout. Otherwise, you have to troubleshoot and do the simulation again until you get the right answer. And for the layout, it is still done using the Cadence EDA tools, and if it is successful, we have to check the design rule. Okay, then only we can proceed to the next stage. Okay, so after the DRC, we have to do the layout versus schematic. This is to ensure that the layout is really representing the schematic circuit. And then we have to do the extraction of parasitic parameters, and we do the post layout simulation. And after we have satisfied that the objective is achieved, then we are done with the design. This is the block diagram of the 13T hybrid full adder that we use. It consists of 3 modules. The first module is exclusive OR circuit, and the output of this exclusive OR is connected to inverter, so meaning that right here is exclusive NOR. Then we have a module 2 which produce the sum, and we have a module 3 which produce the carry out. The input is A and B, and since it is a full adder, we have another input which is C in. So this is the actual circuit for the module 1. The XOR consists of 3 transistors. So this is the output, and that will be connected to inverter before we produce XNOR. And this is the second module. We produce the sum, and the last part, the module 3, output from XOR over here, XNOR after the inverter, and we produce the carry out. So this is the overall circuit of the 13 transistor hybrid full adder. So we are using that 13-3 hybrid full adder over here. We have sum and carry out. The input is A, B, and carry in. So in order to make this hybrid full adder circuit a comparator, we use an inverter over here. Okay, it is connected to the B input of the hybrid full adder, and the carry in must be grounded. And the output sum will produce the A equals to B, and the carry out will produce A greater than B. And if we take these two output and put it to the NOR gate, and we can produce A less than B. So we do the simulation, and this is example of input A and B, and this is the 3 output just now. So when A and B is equal, the output is high. Similarly, right here, 0, 0, the output A equals to B. But if A less than B, meaning that BA is less than B, so right here, output will be 1. And this is when A is greater than B, output is 1. So the output is correct for 1-bit comparator. If we compare the output of 1-bit comparator with 2 example over here is the hybridized full adder module based on PTL and GDI logic. It is using a different supply voltage. It is 1.4. So if you look over here, the power consumption is very high, but for our design, it is 150 microwatt only. But if we compare our circuit with another example of comparator using a 6 transistor multiplexer, this is based on multiplexer to create the full adder, and it is used as a comparator. It is using the similar voltage 1.2. The power consumed by this is much lower compared to our circuit, but it is done in 65 nanometer technology. Another problem with the multiplexer 6 transistor full adder cell is when we cascade this circuit to form a higher order comparator, the output is degraded, meaning that it won't reach the full swing of 0 to the power supply. So that is the problem with this, even though the power consumption is very much less, but compared to ours, even though it is 150.4 microwatt the power consumption, but when we cascaded this 1-bit comparator to form a higher order comparator, we didn't face any problem with the output voltage swing. Okay, in terms of the delay, the proposed 1-bit comparator, which is ours, is 1 nanosecond, and the comparator using full adder of 60 multiplexer, it is 6 picosecond, which is very short delay compared to ours. And the problem is that we have mentioned just now, this comparator will have a degraded output waveform when it is cascaded to form a higher order comparator. So meaning that our proposed comparator is better in terms of the voltage swing, and it can be cascaded to form a higher order. So this is the 8-bit comparator circuit. So we are using 8 full adder right here, the 13 transistor full adder. We need an inverter, 8 of inverter, and this is the AND gate. And the last bit using NOR, we produce A less than B. This is A greater than B, A equal to B. Okay, so this is the least significant bit, this is the most significant bit. Okay, this is the output for the 8-bit comparator. A equals to B, A greater than B, and A less than B. Except for small glitches over here, we have a perfect output swing from 0 until to the power supply 1.2 volt over here, even though it is an 8-bit comparator. Okay, so meaning that we have successfully designed an 8-bit comparator using 13T full adder, hybrid full adder. Okay, as a conclusion, a high-speed, low-power binary magnetic comparator circuit has been designed. The main part is the full adder, hybrid full adder using 13 transistor, and it is done in Cadence EDA tools, 130 nanometer CMOS technology. We are using the technique of minimizing the number of transistor used to minimize or to have a circuit with a less power consumption. Okay, and for the 1-bit magnetic comparator, the power consumed is 150.4 microwatt with a delay of 1 nanosecond. And for the 8-bit magnetic comparator, we have a power consumption of 1.5 milliwatt and a delay of 5.7 nanosecond only. So overall, it can be considered the circuit is has a very good performance compared to other. Okay, so we acknowledge the FRGS grant from under Ministry of Education and to RMC, Nano Simulation and MinSRC. Okay, so this is the list of references. Thank you.